What problem does the proposed method aim to solve in the field of deep learning?
The proposed method aims to solve the problem of unlearning in the field of deep learning. Specifically, it addresses the challenge of efficiently removing specific training data, referred to as the forget set, from a trained model to address concerns such as perpetuating harmful or outdated information, violating user privacy, and other issues. The method focuses on improving the performance of unlearning algorithms by considering factors that affect the difficulty of unlearning, such as the entanglement between the retain and forget sets and the degree of memorization of the forget set examples. By introducing a Refined-Unlearning Meta-algorithm, RUM, which includes a refinement procedure to divide the forget set into homogeneous subsets and a meta-algorithm to dictate how to unlearn each subset, the method aims to enhance unlearning pipelines and address the challenges associated with efficiently supporting deletion requests in machine learning pipelines.
How does the Refined-Unlearning Meta-algorithm, RUM, work? Illustrate step by step.
The Refined-Unlearning Meta-algorithm, RUM, works in two main steps. 1. Step 1. Refinement. In this step, a function f is introduced to partition the forget set S into k subsets, denoted as S_i equals 1 caret k equals fs. The goal of this step is to create homogeneous subsets with respect to factors that impact the difficulty of unlearning and the behaviors of existing algorithms. 2. Step 2. Meta-unlearning. After obtaining the subsets S_i equals 1 caret k of S, a meta-algorithm, M, is required to dictate how to perform individual unlearning requests and how to combine the resulting unlearned models to achieve a model that has unlearned all of S. The meta-algorithm decides which unlearning algorithm to apply for each subset and in what order the unlearning requests should be executed. This step involves executing k unlearning requests sequentially, with each step corresponding to unlearning a subset and composing the resulting unlearned models to arrive at a final unlearned model. In summary, RUM refines the forget set into homogeneous subsets based on identified factors affecting unlearning difficulty and algorithm behaviors. It then utilizes a pool of state-of-the-art algorithms to unlearn these subsets sequentially, guided by a meta-algorithm that determines the unlearning algorithm and order of execution for each subset.
What are the theoretical benefits of using the Refined-Unlearning Meta-algorithm, RUM, compared to existing unlearning approaches?
The theoretical benefits of using the Refined-Unlearning Meta-algorithm, RUM, compared to existing unlearning approaches lie in its ability to address the difficulty of unlearning by leveraging insights into factors that affect the behavior of state-of-the-art algorithms on forget sets. RUM offers a refined procedure that divides forget sets into homogeneous subsets based on factors like the degree of memorization, making unlearning more effective. By sequentially unlearning these subsets using a pool of existing unlearning algorithms, RUM optimizes the unlearning process for each subset, leading to improved overall unlearning performance. This approach allows for tailored unlearning strategies for different forget set characteristics, enhancing the efficiency and effectiveness of the unlearning process. Additionally, RUM provides a systematic framework for analyzing and improving unlearning algorithms, paving the way for future advancements in the field of machine unlearning.
How is the difficulty of unlearning characterized in the paper, and what factors affect this difficulty?
The difficulty of unlearning is characterized in the paper by the entanglement between the retain and forget sets and the level of memorization of the forget set examples. The paper identifies that the more entangled the retain and forget sets are in the embedding space of the original model, the harder unlearning becomes. This entanglement is measured using an entanglement score, S, which captures how tightly the retain and forget sets are clustered in the embedding space. Additionally, the paper explores how the degree of memorization of the forget set affects the difficulty of unlearning. It is found that highly memorized examples in the forget set make unlearning harder, as the model needs to work more to adjust its predictions for these examples. The paper introduces a memorization score to quantify the level of memorization of each example and uses it to create forget sets with low, medium, and high levels of memorization. The difficulty of unlearning is influenced by how well the model has memorized the forget set examples, and how entangled the retain and forget sets are in the embedding space.
What are the experimental measurements used to evaluate the success of approximate unlearning algorithms?
The experimental measurements used to evaluate the success of approximate unlearning algorithms are guided by three desiderata: I, good forgetting quality; E, high utility; and E, efficiency. Forgetting quality is measured by inspecting the accuracy on the forget set, aiming to match the accuracy that would have been obtained by retraining from scratch. Additionally, membership inference attacks, MEAs, are adopted to measure forgetting quality, where the model's characteristics are used to infer if a data point has been unlearned or not. Utility and efficiency are straightforward to measure, represented by the accuracy on the retain and test sets and time in seconds, respectively. The tug-of-war metric is introduced to holistically evaluate an unlearning algorithm, capturing both forgetting quality and utility by comparing the accuracies of the unlearned and retrained models on the forget, retain, and test sets.
What are the key findings and insights obtained from the experiments conducted with the proposed Refined-Unlearning Meta-algorithm, RUM, in the paper?
The key findings and insights obtained from the experiments conducted with the proposed Refined-Unlearning Meta-algorithm, RUM, in the paper are as follows. 1. Refinement alone. The experiments showed that applying RUM-F, where the unlearning algorithm is sequentially applied on homogeneous subsets determined by memorization scores, significantly outperformed both the vanilla approach, applying the unlearning algorithm once on the entire forget set, and the shuffle approach, applying the unlearning algorithm on randomly determined subsets. This indicates that operating sequentially on homogenized subsets based on memorization scores can enhance the performance of unlearning algorithms. 2. Per subset algorithm selection. By identifying the best unlearning algorithm for each subset based on the level of memorization, low mem, medium mem, high mem, the experiments demonstrated that incorporating this insight into the RUM framework led to substantial improvements in unlearning performance. Specifically, on CIFAR-10, applying RUM with the sequence Nothing Raitero Fine-Tune Raitero Salon yielded the best results in terms of both tug-of-war TOE and membership inference attack MEA metrics. 3. Sequence dynamics analysis. The experiments revealed that the order in which the unlearning algorithms are applied can impact the performance metrics. While TOE remained similar for different orderings, MEA varied. The analysis of accuracies on the forget set and its subsets after each step showed that the sequential dynamics of the unlearning process can either neutralize over-forgetting effects or lead to improvements in unlearning performance. This highlights the importance of considering the order of execution in the RUM framework for optimal results. In summary, the experiments with RUM showcase the effectiveness of refining forget sets based on memorization scores and selecting the appropriate unlearning algorithm for each subset, leading to improved unlearning performance and highlighting the significance of sequence dynamics in the unlearning process.